I'm recording on Anpa. And mute everybody. No, that was the wrong button. Mute. That's right. Right, you're all muted.
Hopefully everybody can hear me.
Sure.
Yep. So let me know when, so I'm ready to start then. I'm going to start. Okay, I'm going to keep switching back and forth. So one of the things that I've done, if you can see my screen here, let me see if I can figure out a different mode for this. Okay. A different mode for this is that I put a command line tool like this on my desktop. And so then one of the things you can do with that is you can go in and look at properties, and you can say the start in, and you can put that path to the folder where your geometric algebra is. So you can have a geometric algebra hot link on your desktop if you want. So I've already done that, and this is my command link line here. So let's see, why am I not? Okay. So here it is, and hopefully you can see it. I'm running it, and I ran the 12 test, okay, and I'm ready to go. And I'm going to talk, but I'm going to give every so often if somebody has a question so that we don't have to wait for all of them to the end. But I have a sort of a slideshow that I'm showing that's sort of like, how do I get this so that it's just one window here? Anyhow. So I'm just going to go through these here. So for those, this is just for the video version. So you can go in and download there and download the link from there. And then what we're going to talk about here is the main file is ga.py. This is the main file that has most everything in it, okay? And so I'm going to talk about vectors and multivectors. And essentially what you're doing in Python, they have what's called a read, eval, print loop. And so Python is an interactive system in the sense that you can define variables, and then you can look at them, and then you can do mathematical expressions with them, and you can run functions with them. So that's essentially what I'm doing, and I've built overloading of the Python objects that I use to create geometric algebra with. I've overloaded all the operators so that multiplication and addition and subtraction and division where it's appropriate work in those, okay? So I'm going to show you what that looks like now. I'm going to go over to this geometric algebra here. I'm going to load the geometric algebra tool. And one of the things I told you about is I have this thing called describe. And describe basically tells you is something that allows you to describe something like, let's say, this vector A. So I have this G implementation level, GA vector, and you can see that the variable A is bound to an object who prints itself as A. So this way, anything that you can see in the screen, if you copy and paste it back into the system, it will give you the same values back. So if I say A times B, it gives you this. And then if I mark that and I say, go copy this from this command line tool, and I paste it back in the screen, then that evaluates to itself as well. So I implemented this so what you see is kind of what you get in the command line tool, but yet it's objects behind it, okay? So it's using the read, eval, print loop to do stuff, okay? So I was showing you this describe, and describe kind of gets your bearings here. You know, I said I created all of the variables for A, B, and C, and all the way through Z. And if you go read in ga.py, you can see how I did that. Essentially, I created an alphabet. So there's A and B and C. And I also defined all of the permutations of B times C, and I bound it to a variable called BC. So again, Mike Manthey is used to typing just BC, and he assumes that that's equivalent to B outer product C. Now, all of these vectors are orthonormal, right? Which means that if you do an outer product of them, essentially you raise the grade to grade 2, and this is a grade 3. So as you can see, I've built all of these already, and I've built, you can see all the implementation functions that I have here, okay? And likewise, if you go to the very end, you can see I built them all the way up to Z. So all of those are there. And so you can do A and B, and then you can do A plus B. And what you see when you get A plus B, it's something that looks like itself. And if I describe that, you can, again, looking under the hood, you can see, oh, I have a set of terms that are addition, that are added together, right? This is a GA sum. So this is what's considered a multi-vector in geometric algebra, where A is considered a vector, and AB is considered a bivector, and A, B, C, D, E, remember my convention, where the name is a short version of the something that's bound to the same value, okay? And so once you get used to the naming convention, sometimes we're going to have something called A0 and A1, and those things, the naming is not just one letter, one character. Generally, when I write these, I always do them in bold, so I know there is a vector. But likewise, you can have like DJM is my initials, equal to A. I'm going to show you that you can do mathematical expressions. 1 plus A times 1 plus B times 1 plus C, right? This is thing. And then I say DJM. Well, what is DJM bound to? Oh, I have to spell it right. DJM is uppercase, and so it's a multivector. And what is this multivector? It's the expansion of 1 plus A times 1 plus B times 1 plus C, okay? And so you can see it expands to all of the terms that are the sum of all the terms that can't be combined anymore. So I always simplify these things. And the way you can do this is you can literally do this, expand this out the long way, and then I add all the pieces together, okay? So with that said, you can see that you can easily create all the terms. And in fact, I'm not even going to bind it to a variable. I'm just going to do this, and I'm going to say what's called GA states. The next thing I want to show you is GA states. GA states is this function. Hopefully you can all see my screen. And what it does is it takes the expression, expands it out, and then it prints a truth table. This is just like a truth table in regular Boolean algebra, except here, the truth table is iterating through all the possible values of A, B, and C, where they have values of plus and minus 1. And so you can see that this expression here, 1 plus A times 1 plus B plus 1 plus C, if you expand that out, it gives you this one item, this expression here, a multivector, that contains all of the elements of the algebra, okay? And it has, this is Pascal's triangle, which has 3 of these, 1 of these, 3 of these, 3 of these, and 1 of those. And that's, it's Pascal. And then if I go to A plus B plus C, 1 plus D, you can see the same thing is true. And you can see this has 4 of those, 6 of those, 4 of those, and 1 of those. It's, again, it's Pascal's triangle. You can see it in my dissertation, talk about that, the number of elements. So in order to iterate through all of this.
Doug, can I ask a basic question?
Sure.
Yeah. Remind me, what is a multi-vector? Does it mean that you have 16 rows there? Is that the multi?
Well, a vector is just a single term that's considered, and if you look at its implementation, you can see it says it's a vector, okay? It's just something that's bound to a single value and it has a name, okay? For shorthand notations, I'm just using the letters of the alphabet. An n vector is something like AB, which is a bivector or trivector, and those are called n vectors, okay? They're not a single vector. They have a grade to them. They are either of grade 2 or of grade 3 or of grade whatever, n. So a multivector is the sum of those things of any grade. And as you can see, I put them in standard order all the time for both vectors and multivectors and bivectors, so that there is kind of in a standard order based on sorting names. So you can pick your names so that things are put in normal order. Did that answer your question, Richard?
No.
Okay.
You answered implementation of something. My question is this. in ordinary arithmetic, I think of a 2-vector as a pair of numbers 1 and 2. A 3-vector is a set of 3 numbers 1, 2, and 3 describing a direction in an X, Y, and a Z coordinate system.
Mm-hmm.
And I don't understand how the terminology that you're using, how it fits in a coordinate system like that.
Okay, so what we're doing is A can only have, normally a normal space has a coefficient which can have any value, like the X dimension can be from 0 through 1,000, right? But in here,
Yeah.
A has either A or minus A. It can only be plus and minus 1 coefficients, or 0. And if you take 0 times A, that coefficient is 0, but A disappears because A times 0 is 0, right?
Yeah.
So the point is, it's a premise of geometric algebra that we're saying, look, we're starting as the simplest possible coefficients as we can, 0 and plus and minus 1, and we're working with the hypercube defined by that of plus and minus 1 and 0, and so that way we can kind of keep the arithmetic simple. And in fact, this A is really a bit because of that. It's a bit represented in geometric algebra, where plus and minus 1 means true is plus, minus is equal to minus, and we know that if we do 1 plus 1, we get 2, but 2 is equal to minus 1. So it's essentially a mod 3 arithmetic symmetric around 0. Okay, and I talked about that in my previous talk. So
yeah, I know, but I got
Doug?
the terminology.
Yeah.
Let me another related question.
Doug?
So did that answer your question about coefficients? Essentially, I thought it was a coefficient question.
Doug,
Well, I'm not sure.
wait a minute. Can you hear me?
Sure, I
Yeah.
can hear you.
Lou, go ahead.
He's talking about a vector in his previous education is like 3 numbers, like 3 numbers. So
X, Y, and Z, yeah,
right. So you need to point to him where a triple of numbers would occur here. In other words,
Right.
you have to tell him about how 1, 0, 0, 0, 1, 0, and 0, 0, 1 become a basis.
Okay, I got it. So this is the thing that we figured out when I was working on my dissertation 20 years ago. We were starting with as simple assumptions as we could, and we didn't even assume we had 3-dimensional space yet.
Mhm.
So all we had was bits, and those bits were orthonormal. Each bit, A, B, and C, and D, and E, are ortho to each other, and we just wanted to put it in a form where physics and computer science could use the same language. And
Well,
so
I'm
we
gonna
didn't even assume that we have a 3-dimensional space yet. So maybe that's where we're coming from, because as physicists and traditional mathematicians, people assume there's 3-dimensional space yet. We're trying to build up, starting with bits. These vectors here literally are bits, and we're kind of going to construct in an Anpa-like philosophy, build something out of pure bits. Essentially,
That
that's
part's fine. But having built one of these, I'm now trying to picture it in the geometry I understand.
yes.
So is what you're doing building a whole bunch of multidimensional cubes
Yes.
in which the vertices and the center are the only things that exist? Is that the right
Yes,
way to
that's
think about it?
correct. Yes,
Oh,
that's
good.
absolutely right.
Thank
Very
you.
good, very good summary in your language. Thank you for that.
Yes.
Okay. So that's a great point. And what I was trying to show with this multi-vector example here is that each one of these things is a unique item, and you can't combine C and D as a bivector with anything else. So the only thing we can do is sum them. And this is equivalent to what you would do if you had a Hilbert space where you had 4 dimensions. You can only list the 4 dimensions, and in quantum computing, you would list them with the ket notation, Bra ket notation, as 0, 0, 0, 1, 1, 0, and 1, 1. So again, those dimensions are just a label for orthogonal dimensions. We're not doing anything different here, except we only have real coefficients here instead of complex coefficients, and the only possible values are plus and minus 1. Okay? So one of the reasons I wanted to talk about multivectors is because as soon as you have A, B, C, and D, and I'm just showing this as an example here, you get this here is the smallest addressable item in the space that has A, B, C, and D, E in it. And you can see this because I've iterated through all the permutations of this where A, B, and C, and D have a value, a plus or minus 1. And as you can see, there's 16 possible values here. And you can see that all of these states, I've only addressed one row, row 15 of this. So in order to address the smallest addressable item in the Carnot map or the truth table for this geometric algebra expression, it takes every term. And why is that? Because this math, if you're doing math using this, and I talked about it in my other presentation, you're doing this Z3 arithmetic, what you end up with is that the smallest addressable item is one row in this table, and these rows are all versus a regular Carnot map or a truth table. Those are mutually exclusive in a Carnot in a truth table, but these are simultaneous. And notice here we have these states 0. These states mean that this expression, this state, is not valid in here, and in fact its value is 0. Okay, and this is the does not occur convention. And so you can see of all of the possible values that can be in here, because these things are self-constraining, they only address one item, and this item happens to be +1, a plus in row 15. And so you can see every one of these rows here in geometric algebra literally are concurrent, and of the 16, only one of them is active, and all the rest of them will never occur using this expression. Okay, so that's an important thing to realize, that this is like a truth table, but it's not, because it's concurrent. All of these states are concurrent. In fact, these are linearly independent, and I can take like this expression here, and I can say, take minus so I'm going to say plus, and I'm going to go minus, minus, minus here, just to show you that as I entered these terms, essentially I'm addressing another row in the table by this expansion. And when I do that, and this is using multiplication and addition with the rules in Python, you see now all of a sudden I've addressed 2 rows. This second expression is row 0, the address of address 0. And this is, and notice I've combined them together, and they formed this expression here, which is the common expression that includes this table here, truth table, with only 2 rows in it instead of 1 row. So this is the kind of XNOR logic. It's exclusive NOR logic that ends up naturally occurring in geometric algebra. And this tool naturally combines things, and if 2 things are the same, both of them had this value of AB or ABCD, ABC, right? ABC, all of those canceled, right? And so this thing automatically normalizes it into the minimum form that it can. So I'm just trying to give you sort of like, when I show you this table, what does this mean? It shows that I can create a truth table just like you could if you were doing logic design. You can say, I want this row and this row and this row to have this value, and therefore I can program the equation that I have for this. Now, this particular output column is an orthonormal representation. This representation of, you can think of plus 0, 0, 0, 0, 0, 0 plus as the diagonal of the matrix. It's not exactly like the diagonal of the matrix, but you can think of it as a vector, and I can take the 2 vectors for each expression and add them together, and it's equivalent to adding the algebraic notation. What I call a column vector, it's a row vector notation, and the output of this equation is identical to the algebraic form of this equation, and they're concurrent, which means they're linearly independent, and I can sum them and get the same result as if I had summed the algebra, okay? And this is a nice property of the system, because I can take any 2 geometric algebra expressions and sum them, and it means, and I can that result in this truth table representation. So I wanted to show you the truth table representation because it's important. We're going to use it heavily during this talk. So I wanted to show that to you. Okay.
One more question,
Sure.
Doug. The pluses and minuses in your truth table, they're labeling the vertices, and the value is only in the output column?
Well, essentially, there's an output column, and you can think of the orientation of this entire state, of this entire n vector, can be represented as a plus or minus orientation when the input states are that. So you can think of each vector has an orientation plus or minus, and each bivector has an orientation plus or minus, each trivector has an orientation plus or minus, and the entire n vector has an orientation plus or minus, and that's what that output column represents.
And you're assuming that for each of the generators, its square is 0.
Not
A
necessarily.
wedge, A times A is 0, right?
A times A, since it's a vector, the inner product of A times A with itself is 1. So this, remember.
No, I mean A wedge A.
Oh yeah, well, yes.
And when you're multiplying, when you're multiplying 1 plus A plus 1 plus B and so on,
Yeah,
it's the wedge.
A wedge A is the outer product, and yes, since they're collinear, A with collinear with itself, its outer product is 0.
Right.
So by
I just thought
definition,
it's worth mentioning that because
absolutely.
when you multiply.
Absolutely. And in fact, if you take A times B, A times B is really the same as A dot B plus A wedge B. This is the formal definition of what that is. And I have to say inner here. I don't have, a syntactic convention for that. And as you can see, the inner product of A and B is 0. And the outer product of A and B is just the bivector AB. And the reason is because the geometric product is literally the inner product plus the outer product. And so things that are orthogonal grade go up a grade, and things that are inner product related go down a grade, or down to 0 if they have no common terms. So, okay, so just realize that the definition, literally the definition of this geometric product is the same as this, knowing that if A and B are always orthogonal, that this simplifies down to the outer product. Okay, so that was a good point. Thanks, Lou, for that. I'm going to go back to my slideshow for a second here just to remind myself what I'm going to talk about next. So we've kind of like given you an introduction to it, and we're going to show you an example of how I can use this. I'm going to go into what's called rock, paper, scissors. This was one that Mike wanted to talk about. I'm going to bring up my editor here a minute. And what I figured out was, because, and I'm going to bring up that example here. Okay, so I'm going to show the file, for example, here. So what I realized is if I had taken these expressions here, I defined a bunch of vectors, this GA space, these are the GA states. And if I look at that, this is the list, okay? And if I say, go get me the GA states on this, on that list, I can't just pass a list, I have to add a sum of those. Then I get this table that's 64 elements wide and 64 elements long. And the reason is because I'm putting them in normal form. I have player 1 plays paper, player 1 plays rock, player 1 plays scissors, and then player 2 for those other ones. So what I did is I found that these certain rows of these represented what I would consider the answer for this problem. And I found that those were row 10, where row 10 is a case where one of the I can essentially code a plus or minus in each one of these, and I can say, I want this rows to win under this situation. So I program this table, and I can say RPS. So I have RPS here, which is of all of these individual results. And if I say row states on that, I'm just using this as an example of sometimes it's weird to look at this stuff, but you can, well, let me compress it a little bit. I can say I don't want to show the zeros. Okay, and as you can see, this is the case when there are some don't care cases in here, because I programmed this to be only worrying about the ones where there was 2 pluses, one for player 1 and one for player 2, and this is a don't care. And it turns out for these states, they will never occur because these 3 inputs are mutually exclusive and these 3 inputs are mutually exclusive. But if I say this one here has a scissors and this one here has a rock, I can say then player 2 wins. I've defined this as being a plus means player 1 wins, and a minus, which is +2 essentially, and -1 is +2, player 2 wins. So I've defined this program to be like that. Okay, and so the point is now I can actually play it, and I can say play rock, paper, scissors, and I can say I'm going to pass in a rock here and a rock here, and I can say, oh, it's a tie, okay? And I can do scissors here and player 1 wins, and I can do paper here and player 2 wins. Okay, so what I did is, here's an example of applying geometric algebra to solve a particular problem. And the way I did it is I looked at the entire truth table, programmed the rows specifically that I wanted that showed one input set, and the other says if this is if S1 is there, then set this to be that I want this to be a plus, that player 1 wins. And if, excuse me, notice the minus here. This says I want player 2 to win. And this minus here says I want player 2 to win. And the one with the plus in it says I want player 1 to win. So this is the entire state of it. And then I evaluate it. I say, given the 2 players, this is the entire code that actually runs that algorithm. It's like executing a truth table. And I do that by essentially using eval. I cheat here, which is a Python thing. And I essentially create a local copy of these variables, bind the values based on player 1, player 2 selection, run this and simplify it into the result, and then choose whether player 1, player 2, or tie. Tie is when a 0 is returned. Okay, so you can see here's a concrete example where I can apply geometric algebra to do things that we would use Boolean algebra for. And here's an example of rock, paper, scissors. Okay, also did the same thing with rock, paper, scissors, lizard, Spock, which is a version from Big Bang Theory, where instead of having only 3 terms, this has 5 terms, and you have a total of 10 rows of possible combinations of these, and you get a total of 20 expressions when you do this. And you can do the same thing with this, and as long as you limit the inputs to be mutually exclusive, then you're fine. You can just put plus and minus 1 in the inputs, and you run this expression, and away you go. So there's an example of applying geometric algebra where you're looking for a specific truth table, and you can get a specific result, and it works. Okay. This was interesting to Mike because it turns out that even though I programmed this thing to look really weird, the final result looked almost like I programmed it. And the reason is this has 3-way symmetry in here, and all the other terms cancel out. And so it's interesting that some expressions don't blow up when they're running concurrently. This is the concurrent execution of the outer product of these bivectors, which is kind of interesting, that it's the rules are that simple for this particular example. This was an astounding result from that. Okay, so I'm going to go on to the next slide. So we can continue. That's rock, paper, scissors, lizard, Spock. The next one is I'm going to go talk about qubits. Okay, so that's that one. You can also type in, if you're you can type in CLS, which is clear screen, and then you can say I'm going to go run This is time I'm going to go do qubits this time. So I'm going to run the qubits example. This time here now, I have A is bound to qubit A, B is bound to qubit B, and A times B, which is the geometric product. This is geometric product looks like tensor product in geometric algebra because I'm taking all the permutations of those, and what I get, this looks just like the ket notation. This is ket 0, 0, this is ket 0, 1, this is ket 1, 0, and this is ket 1, 1. So this is identical to the looking of it, but the only difference between this and geometric algebra versus Hilbert spaces is in Hilbert spaces, that notation is actually a vector notation. But here we can see that they're actually bivectors. And this is important because we're going to see in a minute here when we talk about entanglement that, so the other thing we have is this thing called SA. SA essentially is a spinor, and we know that SA times SA squared is -1. So SA is like imaginary number, but it's specific imaginary number for these two dimensions, A0 and A1. So with that, since I now have A, I'm going to do GA states for this, so you can see what's going on with the GA states. Let me type here of A. I'm going to say, okay, this is a qubit, and you can think of this as in the classical state where A0 and A1 are opposite values, so it kind of looks like classical bit, even though it's a qubit. And I can go in and rotate that by multiplying it times SA, which is the spinor, and it spins that. It multiplies SA times each of these elements and summarizes it. And now it's flipped it so like it's gone from the classical looking state to the superposition state where they're both plus plus and minus minus, okay? And if I do it again, and this is essentially what I did for my dissertation, I showed that this looks like a qubit. And as you can see, the state by multiplying SA times it twice, essentially I've rotated it around now where instead of having plus and minus, now it's minus plus. So essentially it's the inverse of the original state. And so, so you can see that this qubit looks like a qubit, and I have a spinor, which is, this is the Hadamard transform in geometric algebra. Okay, and it's the equivalent of this not the inverse, minus A is the inverse, but A times S of A is spin 1/4. You know, it's 90 degrees instead of 180 degrees. So this is the difference between not and inverse in geometric algebra. It's the same in Hilbert space. It's no different. In fact, the notation almost looks identical. I'm just using vector names that have A0 and A1 instead of ket notation that Hilbert space does. Okay, so as you can see, what I did for my dissertation was showed that this here, where A looks like this, looks like a qubit. Okay, it's not assumed that I've embedded it in three-dimensional space. You're not going to see a block sphere. But if you look at this, if I look at this and I look at GA states for this, remember what I was saying earlier that that GA states, if I spell it correctly here, that it has these two rows, and these other two rows do not occur. That's what 0 means. So essentially, this expression here can be broken down into the expression where this state is concurrent with this state. So I could expand this out, and you can see that this is much more complicated than this simplified expression would be, because it's the sum of two linearly independent states. And I could express that out, and it would collapse back down to this state by this, okay? But what this means is that because this particular row, remember what I said here, A1 plus A0, 1 plus A1, that one row in this table contains all of these items. Well, this is important because look, to address one row in this qubit space, I have to have all possible n vectors in here, which means that in order to express this, as soon as I have A0 and A1, I also have the spinor of A0, the outer product of the outer product of A0 and A1 too. And so this forms a space that has 3 items in it, which is the exact same thing as a Hilbert space, except that Hilbert space has 2 vectors with coefficients that are complex numbers, but with the unitarity constraint, one of those are redundant. And so really it's only a 3-dimensional space as well there, even though we think of it as a 2 dimensions with complex numbers in them. It's the same number of active dimensions in here because this bivector is assumed to be part of the state space that's defined by A0 and A1. Anytime you have 2 vectors, you also have all the permutations of those to get to an individual row in this truth table. And therefore, by definition, you can assume that all the bivectors and trivectors that are needed to express it are also there. So combining A0 and A1 together is more than just addition. It assumes that the state, that the G2 or G3 defined by having those 2 terms communing creates all the subterms and all those other expressions in the system. So that's why the 1 plus A0 and 1 plus A1, this shows you all the terms that are actually there in case you didn't know that, okay? So I'm gonna go back to the slides here. So we talked about that, and we've talked here about looking at, we talked about these in the middle here, A times S sub A, and we talked about A times S sub A twice, and we're even going to look at this, we're going to look at a minute here, S sub A itself. You can see it looks just like this. Since it's a single vector, there's no zeros in here. But as soon as you have an n vector, you have 0 terms, and so some of these states do not exist in that expression. Okay? So what we're going to do is talk about roots of unity, because what are we talking about here when we say we have S sub A squared is equal to -1, and S sub A to the 4th power is equal to +1, okay? Well, it turns out I have this tool called GA-solve. And what GA-solve does, it says, look, go find, for this expression here, I'll show you here. I'm going to say, for the state space defined by A0 and A1, go through all the permutations like I just did with the truth table, but find anything where this is a locally defined function, but you could create a globally defined function too, lambda. This is what Python does. It's lambda calculus, essentially where it says where lambda of x, where x squared is equal to -1. So we can do these kinds of things. And so I'm going to do that here. A0 and I'm going to say lambda x, where x, this is the square indicator with the double star, is equal to -1, okay? So I can put a second expression there, or I can put a constant there. Oh, sorry, I had to put a different term here. Okay, and so what this does is it iterates through them. It iterated through all 81 possible states. And why 81? Because there's two, if we look at this expression we did up here, there's 4 states, but there's 9 total states for a single vector, constant, with constants, and I showed this in the other paper that I gave the other day, and 9 squared is 81 total states for G2. For G3, it's 81 squared total states, and it's 3 to the 2 to the n, where n is like 1 to 1 like this. So there's 9 states for 1 qubit. For 2 qubits, there's 81. For 3 qubits, there's 6,500. And for 4 qubits, for four vectors, there's 43 million states. See how this is squared each time? And this is because there's 3 coefficient values, and there's 2 to the n number of distinct elements in the algebra. Okay, so that's where the 81 came from. So if I go back to GA solve here and I say, show me all the expressions where x squared is equal to -1. Well, as you'd expect, you would find all the bivectors in there, which you do. But you'd also find this where I'm using the state of a qubit as an operator and squaring it. So here I'm going between operators and states, and I'm saying, well, A0 plus A1 also squared is also equal to -1, which is an interesting thing to know, okay? But I also can say, well, go tell me where they're equal to 1. Well, to me, or this is the other one, 0, okay? So what we're finding here is that in geometric algebra, it's easy to write something like GA solve, and you can iterate through all the 81 possibilities, and you can say, oh, tell me where some mathematical expression is true. And so Mike and I use this heavily to go and find things. And one of the things we find is when something is equal to 0, it's nilpotent. Well, this is a different nilpotent than you guys are doing because we don't even assume space and time exist yet, nor energy exists. We're just looking at nilpotency associated with 2 bits. And those 2 bits look pretty close to a qubit from our perspective, but it's not embedded in 3-dimensional space yet. So we're finding that this state, A0 times A1 is like a boson, essentially. It's nilpotent. And Mike and I believe that these terms here are nilpotent, that these are the W and Z bosons. But what this says here is that these bosons exist in only 2 dimensions. And that's this diagram that I've shown here before that you guys may not have understood was this expression here where I showed this expression here. It says, if I have only 2 dimensions, G2, and I don't have any space and time yet, just have 2 bits, what do I have? I have a qubit, but I also have these expressions here that look like what we consider bosons because they're nilpotent, and these things here that look like particles because they're unitary. So that's what I did here a minute ago. I said things that look like 1, these here are the neutrinos. We believe these are neutrinos, and we believe neutrinos are also in G2, which makes them understandable why they're so hard to measure. It's because they're not 3-dimensional objects. They're only 2-dimensional objects, okay? And we're going to talk about neutrinos some more in later, but basically, if you were to take these, each expression for something like a particle, like where something is equal to this, its and its inverse are like the particle and antiparticle, and they cancel. So you get, if you take this and its inverse and you add them together, they go to 0. That's exactly what happens with a particle and antiparticle. They totally cancel each other, and the net result is 0 structure from this perspective. You don't have a neutrino anymore. Okay, so this is the kind of, again, we're just interpreting these simple mathematical states and looking at what kinds of things we see. And one of the things that we see is this -1 also. So we're kind of covering some of the material that I was going to talk about in a minute here. Let's go back to my slides. So that's what I just covered was the roots of unity. Let me show you that. And so you can see, we also can find something that looks like x squared is equal to -x and x squared is equal to x. But we can also look at something like this where x cubed is equal to +1. This is a trine state. It's a phase 120 degrees change, and these states all come back around to 0 after, this is why Mike calls this roots of unity, the cubed root of this, which is a trine state. And if you have a qubit, you better have a trine state, and we do. And it looks like this. It has, the bivector is part of the operator. So, so this is the trine state, and this is this is the square root of naught. Essentially, x to the 4th is +1, and that's what these are. Okay, and So you can see that we can get the roots of unity. You can get the bivectors. You can get the neutrinos. You can get the, and you can even get x squared is equal to x. Now, we're going to see here in a minute here, these are all the nilpotents, unitary and idempotents. And one of the things that we learned here is that that you can have lambda squared. This is x squared is equal to x. Well, this here is an idempotent, and an idempotent is specifically associated with measurement, okay? And it turns out that the idempotent, we can show here in a minute here, this here is that for x squared is equal to x, which is the idempotent, and if we assume there's a unitary for u squared is equal to u, which we think is the particle, then we can prove that x is equal to -1 plus or minus u. And the proof is you take x squared, you substitute u in there, and you get x back again. And so we believe that if you have something like x squared is equal to x, it's directly related to the unitary things, and that particles and idempotent behaviors are connected by this formula. Okay, so anytime you have a unitary where x squared is equal to 1, and we think that's a particle, it persists, then you have a measurement operator too, which is the idempotent that matches it. And this is true for any geometric algebra that we've looked at so far. Okay. So what's the net result of this? This is a table directly out of my dissertation. And back then I didn't know as much as I know now, but I kind of put labels on these things. And all I did was say, well, look, what is minus x? What is the inverse of x? What is x squared? What is the square root of x? And if I could find those things, that I could show where something squared is equal to this. And this is sort of my summary of it. And I've sort of labeled these things. And we see that this is like a qubit plus or minus 1. That's what that means. This here is actually the inverse is, this is the inverse here. And this is the spinner. So the Pauli spin literally is one of the noise ways of creating noise in qubits. This is the sum of both the regular invert and the Pauli and the spin and the logical invert and the additive invert. It simultaneously do them both at the same time, and I have a whole section in my dissertation where I talk about the Pauli spin and the Pauli noise states that you can get. And this actually measured that. So the other thing we have, these things are idempotent, but they're also, as you can see here, they're a sparse version of plus and minus 1. So imagine that you have a diagonal on a matrix and it was all pluses, plus ones or all minus ones. Well, what if you only had half of them plus ones and the other ones were 0? What would that be? That's what equivalently this is. And we're going to show you in a minute why that happens. Essentially, if you're embedding states in a dimensional space, some of those states never exist, but the ones that do exist are all plus 1. So it's a sparse version of plus 1, and it shows up as you're embedding things. Okay. So this is sort of right out of my dissertation from 20 years ago. And you see the trine here, you see the Pauli spin, and we see what we think is the neutrino and antineutrino. And you can see because it comes out of these properties of x squared and the square root of x and things like that. Okay. So one of the programs I have out there is called particles, and if you run the particles thing, and we'll run it in a minute here, there's a section on there called neutrinos, and so I run these because we think these are the neutrinos, and it's where this state is true, and these are unitary. Okay, but when I did my dissertation, I realized that these were also the eigenstates for this qubit. Okay, and these Rodi codes were related to the eigen, and the projection operators were also related to these. So it turns out these neutrinos here are related to the mathematic fundamentals of the qubit. But if you put it in this kind of organization, the way I did the other day, you see that this is the equation form of it, and this is the output column version of that. You can see these things all line up where only one of the states is 0 and all the rest of them are minus, or likewise, all of them are, one of them is 0 and all the rest of them are plus. And if I put them in this kind of order, if you sum the 3 above it, you have 2 minuses, you get a plus, 2 minuses, you get a plus, 2 minuses, you get a plus, and then, excuse me, and then this last state is it gets a 0 because you get 3 of them, right? Minus, minus 1 is plus 1, and plus 1 and minus 1 is 0. So the sum of these three vectors is literally this other state. Well, this other state has the same property as these others do. So we believe, if you look at the GA states of it, this column here, not just the algebraic expression, that there's 4 neutrinos, and the 4 neutrinos, that the particle is the sum of the 3 antiparticles. And likewise, the antiparticle, the new antiparticle, is the sum of the 3 particles. Now, maybe in the physics, we've never been able to distinguish these very well, but we don't know if you should be able to find this in the lab. But this will be interesting to explore whether there really is a 4th neutrino and antineutrino pair, just because these are all the possible states. Excluding this one doesn't seem to make sense, that it's there, it's a real state, and it's just, and you have neutrinos and antineutrinos showing up in here, okay? And I just use by convention, assign labels to them, but they may be that the labels are flipped. Okay? So let's talk about quaternions. So it's easy to show I, J, and K that you can go in and you can create a 3-dimensional space essentially, but remember, if you do a 3-dimensional space, Y is equivalent to minus YZ because of the orientation. But in the quaternions, it's actually oriented, it's not oriented that way. It's not oriented around a volume, it's oriented as a group. And so I've typed this in earlier, and you can do it yourself. Q sub I is equal to X, because I have X all the way through Z defined. So I can define these, and I can take the sum of these, and I can square the sum, and I can take the multiplication of it to get minus 1, and I can multiply any pair. Comma means it's a list, contains 2 items, and I can show that the product is equal to the other one. And so this is the quaternions. It has a complete definition of quaternions, and quaternions, I, J, and K, can really be just defined as bivectors. But what's interesting about this is the quaternious sum is nilpotent. And you go, well, why is that? And this is easy to show here, and I'm going to show that here. So if I have A and B and C, and I take A plus B plus C, and I square that, I get 0. We believe in G3 that this is a photon because it's nilpotent. Okay? But if I take A plus B times C and I multiply it out, geometric product times the pseudoscalar for ABC, I get this. Okay? Well, this thing here also is nilpotent. So the sum of the IJKs of quaternions is also nilpotent. And why is it? Because it's a rotation of another nilpotent. And a nilpotent times anything else, if you square it, you still get a nilpotent. Okay? So here we can show that, just like I wanted to say here, is that this sum here is nilpotent. This might be the X17 boson that somebody's been measuring. Think of it as space itself is a boson. And you can see this simply here because the sum of the quaternions is just a rotation of light. And so where you can say, well, how did you find this, Doug? Okay, I'm going to go back to that expression here. I'm going to do GA solve. And I'm going to say for terms A, B, and C. This time I'm doing it in 3 dimensions. And I'm going to say lambda x, where x squared is equal to 0. This is the nilpotent look, but instead of only G2, this time I'm doing it for all of G3. And these are all the nilpotent forms in G3, and there's 6,500 of them that I'm just iterating through. And notice this doesn't take too long for 6,500. But I've also done this for G4 with 43 million, and it takes about a week to run this. So realize this is real computer science, and in fact, I've sped it up using a version of Python called PyPy, and it's built in, and it says, out of the 6,500, I found 81 nilpotent items, and you can look at these items, and this is the Meson, I can't pronounce it correctly. This here is the, we believe these are mesons. And then we also see all the variations. This is the photon. This is the W and Z boson that is showing up at the lower dimensional space. It's also showing up in a higher dimensional space. And you can easily find out where all these nilpotent items are. Notice, I haven't assumed that space and time exist here, even though I have 3 dimensions of A, B, and C. These are just bit vectors. I haven't invented space-time yet. All I'm doing is saying I have a 3-dimensional orthonormal space plus and minus 1 unit cube with 3 dimensions in it. That's all I'm saying here. And it has these properties. Okay. And likewise, I can go do the same thing and say, go show me all the things that have 1 of them. And these are all the unitaries. And we believe these are all the particles. And we believe that this here is the proton. And the electron shows up in here too. The electron shows up as, this is the electron right here, AB minus BC, all the variations of the sign of that. We think that's the electron. So as you can see, it's easy to run this stuff now. Again, we found 92 variations of this, and it's built totally on the symmetry of the space. Okay, so I'm going to go back to my slideshow again here. So, you guys can play with this as well and figure out, well, what does this mean? Okay, so let's go. So I talked about that. I talked about the neutrinos. Let's talk about the quaternions. Okay, let's talk about these, what I call the concurrent spinors. Okay, we're going to look at S sub A, and we're going to look at S sub A and S sub B. Okay, so let's do that. So I'm in qubits. So I'm going to have, I have S sub A, which I predefined as the symbol called the spinor for A qubit, and I have A as the qubit, and I have S sub B, which is the spinor for qubit B, and I have qubit B. Okay, so if I say GA states for S sub A, you find out that it's just a bivector, okay, and it's all the states are there. But what if I say, give me the GA states of S sub A plus S sub B? This is one of the things I did in my dissertation. And notice, as soon as I have a sum, some of these states cancel and they go to 0, okay? And so if I suppress the zeros,
You have a period where you want a comma.
yeah, that's right. Don't have it. Okay, so I'm getting rid of all the 0 states. What you see here is I'm doing the concurrent sum of spinor A and spinor B. But what you see here is that the only time it's a plus as an output is when only one of the qubits is in a superposition state. In other words, that it's causing B and B sub 0 are in inverse relationship rather than the sum of them. In other words, here they're both the same, so it's minus. But if either one of them is inverted, then that's a plus. Likewise here, and likewise here, it's minus again. So it's a plus. It sort of indicates which one is in superposition and which one isn't. So if I now go in and say, look, go in and take A times B, which is 2 qubits. Remember, we did this before, and we get, these are all the possible Hilbert space, just looks like a Hilbert space. But then I multiply this times, this is geometric product again, S sub A plus S sub B. Okay, what you see here is, I'm going to go comma again. Notice that now instead of having 4 dimensions, 4 possible terms as the output. I only have two of them. So this is, I have A0, B0 and A1, B1. Well, when we first looked at this when I was working on my dissertation, I realized that this was the Bell state. This is the Bell state, which is equivalent to ket 0, 0 and ket 1, 1. Okay, this is one of the Bell states. And this is inseparable, and it's entangled. Okay, and so by having done this, I proved that this is the Bell operator, SA plus SB is the Bell operator for this. And if you look at the state of this, you see that it self-selects only items where one of the qubits or the other one is inverted. In other words, all the other ones are 0. So this says B0, B1 is in a superposition state, or this one is in a superposition state, or this one is in a superposition state, or this one is in a superposition state. It shows that it's a simultaneous concurrent spinner of essentially I've rotated something that started out in what I would call the classical reference frame, where something was both the two states were opposite of each other, which is what coordinate of the qubit state it was in. And I moved it into a superposition state, so it was in 0, 0 or 1, 1 state. And as you can see, this self-selects these two to be, this output column is really, and the fact that there's zeros here, it only says that these are only true when one of the qubits or the other qubit is in a superposition state where their states are opposite of each other, okay, rather than to be the same, which is more of a classical state. And so this operator self-selects the superposition states of both qubits combined. Well, this is interesting as enough as it is, but if I just look at this state here, say, okay, let me look at it squared. What you see is this thing that looks like all minus 1. So this expression here, plus 1 minus a, this here is the pseudoscalar for this G sub 4 that contains these 4 vectors. And this state here is equivalent to minus 1, a sparse version of minus 1, because you can see it only has minuses here, and the other states are 0. Okay. And in fact, if I say this 4 times, you will see that it's all plus 1. And in fact, there is an expression here I can do. I can say that plus and I'm going to take the minus here. This is like the complex conjugate of the Bell operator, which is the magic operator. You can see I get plus. So I have a sparse version of the Bell operator is equivalent to plus and minus 1 by a factor by taking the power of it to two times, or power of it for 4 times, which means that some operator, some state A times B, and if I multiply it times the Bell operator, well, if I multiply it times the Bell operator, first of all, I get, go back to here, I get a smaller state. But once I'm in that state, this state here, I stay in this state, and I keep going between all the Bell states. In fact, I can go, oops, not times 2. This is another Bell state. This is another Bell state. And this is another Bell state. And this back to where I started from. Okay, so if I go back to 5, then I'm back to where I started, and I'm back to the original state I started. So the Bell operator acts like a higher dimensional version of the Hadamard gate, where it goes around the circle 4 times and it backs to where it started, okay? With one exception. It's in a higher dimensional space, and it got rid of 2 of the terms, okay? And this is easy to show where these terms went to. It's due to the multiplicative cancellation. If you have this state here and you multiply it times that, 2 of these states disappeared due to multiplicative cancellation. Well, you can show, and I show in a minute here, that you can think of this as these four states are the sum of two Bell states and two magic states. And two magic states and two Bell states, a Bell state and a magic state summed together is the normal state of a qubit. And when you multiply it times a spinor, this Bell operator or the magic operator, the state, the Bell state times a magic operator always gives 0. It's multiplicative cancellation. So that's really, we can show that, and I can summarize it that way easily. And we can show it that these, not only are they concurrent spinors, but they do multiplicative cancellation. And we get these two states disappearing, okay? And I showed this in some of the other conversations that I did. I think I have this other presentation that I did where I showed that. Yeah, I did this slide here where I showed that here's the Bell states, and those are identical equivalent. These are just like a notational difference, but it's identical to the states of the Bell operator states. And I've done this in Hilbert space as well. I know they're exactly the same thing. And you can't factor this. And the Bell and operators are irreversible. So how do I know that? Because in my dissertation, starting at page 110, you can show that there is no expression such that 1 over this Bell operator exists. And I can prove it in geometric algebra. And I exhaustively proved it by running for several weeks that there's no expression that you can have out of the 43 million possible states, that there's no possible operator that is the inverse of this. Okay, and that's true for both magic and Bell states, which is plus or minus this. This is the complex conjugate if you use the minus. Okay, and the reason is because these two states are the magic state that we found up here, and the states that are underlined are the Bell states, and the states that are not underlined are the Bell magic states. And if you take any of these complex conjugate kind of relationships, you find that anything in one set magically does cancellation on the other set. And so here's where bivectors produces a result that you can't easily see in Hilbert space, because Hilbert space doesn't have bivectors. The other thing Hilbert space doesn't have is you can't use operators as states and states as operators. And here I'm using what looks like it could be a state, but it could be an operator, but I'm using it in both cases here as an operator. And you'll see in a minute here that we're going to use it as a, interesting is if you do the same thing with higher versions of qubits, you get the same result, except that instead of taking 2 to the 4th to get around, x to the 4th power to get back around, it takes x to the 8th power to get around. It takes longer to get back around because it's a bigger space. Okay, so roots of unity, pay attention there. So I'm going to go back to my other slideshow here. And I guess I'm running out of time here, and I'm almost to the end here. So let me show you the last couple slides on my talk. So once you realize that we can do what's called quaternions, you can also do tau-quaternions. And essentially, these are complex conjugate pairs that look just like quaternions are, except that they're the sum of two bivectors instead of just a single bivector. And we can show that this is true, and we showed you why we needed this sparse invariant here, because you can see they're minus, minus, minuses, and plus, plus, plus. We showed that already, okay? And I showed this expression here, b to the 4th plus m to the 4th is plus 1, okay? And you can use this little helper function, report 4, that reports all of that information at one time. And it shows exactly like, this is exactly the definition of quaternions, but in higher dimensional space. And these B and M operators can be used as states. Notice magic and Bell are inseparable too, just like these other ones are. And these tau-quaternions, if we do this, we're using something that's considered an operator as a state. So the Bell and magic operators are actually the state as well as an operator. And you can't do that in Hilbert space. So, but what this gives you is the tau-quaternions, and you can easily write a program. There's a program out there called tau code I ran. If you just run it, it prints all this stuff out. And part of that printout is it shows you the Bell and magic states, and it shows you these are the Higgs. Now we're going to talk about the Higgs here in a minute here. So we talked about the sparse invariance already, and here's the examples. You can run these. It's easy to run these. Here's the examples. I'm running out of time, so I'm just going to go through them. And you can show that, I think I already showed you this, the Bell and magic operators. Yeah. So the point is these Bell operators and magic operators you can't factor them. They're separate, they're singular. You can't find an inverse of them. And so these states, due to Landauer's principle, are stable in the sense because these states here, information was erased to get into this state, and they're singular. So in order to get out of this state, you have to add that information again. So this is a different result than Hilbert space gives. Hilbert space shows the Bell operator, which is the higher dimensional version of the Hadamard, and the control knot is invertible, and this one is not. And the reason is because it's a bivector rather than vectors. Okay, and so this is the net results of that. So the only other thing I'm going to talk to you about is the particles thing. I'm going to run this and then I'll be done. So if you run this particles thing, the first talk I gave you a summary of all of the particles that we and I came up from nilpotent and idempotent and unitary. And essentially this computes all of that, and it shows you, if you just run particles, it gives you a summary here. It says for G2, this is what we found. And this tells you the states that we found. This is the nice little summary at the end. It tells you where the quaternions are. We have neutrons, electrons, quarks, the spinner, which is the Q-trit, which is we think is the photon. This is a spinner 3. It's Mike thinks it's the electrical primitive in G3, where in G2 you only have a bivector, so you don't have a three-dimensional item. So we believe that magnetism is two-dimensional, which is why you can't have a magnetic monopole. But the electrical root, the pseudoscalar for electrical is G3, which means you can have a three-dimensional version of that. And so this is sort of the summary of all of that, and why we have this chart here that looks like this, because we believe that when you get things by the grade that they're in, you get this kind of organization of the standard model. And I've done all the Higgs. We could talk more about the Higgs, but basically the Higgs is the complete even sum algebra of G4, where the sum of those squared is 0. Okay, so they're nilpotent, and there's only 16 of them, and so I think we'd have to go to another slide, but that's what that one was, the Higgs. These are those states. There are 16 of them. These are the Higgs, and it's where h squared is equal to 0. But these are the sum. These are three pairs of tau-quaternions summed together, which is like quark math for the Higgs. Just like quark math gives you protons, the tau-quaternion tri-summation gives you the Higgs. And notice it's all even subalgebras. Okay, and so the Higgs, anything that has bivectors in it, and it wouldn't necessarily affect anything that has even grade. So that's sort of how we found all this is by using this class of tool. Okay. So with that, I'll say I'm done, and questions and answers, and we can look at something else if you need to. I can set up specific times with people to go through specific things if they needed to at a later date. So.
Okay, thank you,
Go
Doug.
ahead.
Um,
I'm
you-
just
if you
sharing
stop,
now.
if you stop sharing now, Lou's got a question.
Okay. Let me see. A couple of questions. One of them is, it seems to me that your your program based in Z3 is
Yeah.
finding a lot of fundamental patterns and enabling you to go through very, very large combinatorial spaces and explore them.
Yep.
And if you could couple that with a version of the program or a little tweak on the program that would let it also work with these algebras over the rationals or the real numbers,
Sure.
then it would make it possible to interface these same patterns with things that other people are using. So,
Right.
for example, I find that in matrix algebra that the Bell operator is decomposed as an identity plus plus a square minus one operator, and
Right.
and all that kind of structure you're talking about it extends to an algebra involving the braid group and so on.
Yeah.
I can't work over Z3 to see that. I need to work over the real numbers.
Mm-hmm.
Or another example is with nilpotents, where if you go over the real numbers, then you find that the same stories about the nilpotents lead you to the Pythagorean relationship,
Mm-hmm.
which is fundamental to relativity. So
Yeah.
if the program could be tweaked so that a user could go back and forth between doing an experiment, a clear experiment over Z3, and then shifting to see what it corresponded to
Yeah.
over the reals, it would be quite fantastic.
Yeah. Mike wants the same thing because he believes that our quark math needs to be Z5 instead of Z3. You can't add two quarks at the
Yeah,
same
it might be
time.
another cyclic group could be important
Yeah.
as
In other
well.
words, if you take two quark, some protons like mesons are the sum of two quarks. Well, those are easy if they're different,
Yeah.
but if they're the same, all it does is it produces an inverse of itself. So you don't have two
So
quarks anymore.
so that was a suggestion, and the other is a question. Do you have a hint about how to do particle interactions for your particles over Z3? What the particle, what interactions of particles should be, and to do computer experiments to find out what you get for your particles?
Yeah, that would be something that would be interesting to do. Um, in that file I sent you, there's a thing called Majorana, and it's been so long ago since I worked at it that Majorana is a particle is a particle that might not actually be a particle, but it's where the antiparticle and the particle are the same. And so there's a program out there. If you run it, it tells you about what Majorana as a higher dimensional version of other particles. Okay, so essentially we're working on where the light is good, looking for things where the light is good,
Yeah,
under the street light. And we're finding
right,
things that we already know how to do in the program that we have. And Mike and I keep
right,
coming up with things like rock, paper, scissors. We go, Mike
yeah,
says, there should be mutex in there. And finally, I was able to figure out how to do it after scratching our head for 2 years thinking about rock,
right,
paper, scissors.
right.
So
But
all these are
there
good
is another
ideas. And I
place.
would encourage
There is
working with
another
somebody
place.
who wants to work on that. Yeah.
There is another place where the light is good, and that is Peter's work,
Yep.
where it's algebraically so close to what you're doing.
Yep.
And Peter's work does tell you about particle interactions. So there's some decoding and decrypting that's
Yeah.
needed in order to go back and forth. I think it'd be really worthwhile to work on it.
Yeah. I think that the towers need the towers need to talk to each other. Yeah. And I know you guys are doing good, real good. That's no objection. And I'm not trying to say that anything's wrong. I'm just saying we're getting different results than what Hilbert space does. And why is that? And the only difference is that we don't assume that space-time exists yet. And we're not even talking about energy yet.
Yeah.
So we're just looking at pure topology in a bit space.
Yeah, well, whenever you have a vector space, you can always take the Grossman algebra corresponding to it. So you can go there, but
Right.
this seems to be a really, really useful thing to do
Yeah.
in this case.
And you can see it's pretty fast
Mhm.
for the stuff that we're doing in G3, so. We don't know how many dimensions it takes to actually get to 3 space plus time, 3D plus time. That would be another thing that I would want to do. And that's maybe what Peter's doing and showing how once you embed it in, space-time is emerged from bit spaces, what is that? And that's something that we're interested in as well. So obviously, the entanglement is where all the good light has been. So that's why we keep working on that areas.
Any other questions?
Thank you.
Thanks, Lou.
Anton.
Thanks, Lou. Appreciate your comments and question.
Yeah.
Now you know why us to work together.
Anton.
Yeah. Doug, I must admit I only understood 5% of what you've been saying, you know. But in my ignorance, you know, of what you're doing, I don't see the physical connection between some mathematical vector space and the particle or the physical world. You know, could you sort of guide me why a vector space should be a particle?
Well, even if you look at Hilbert space representations, it's just mathematics. So the question is, which mathematics do you believe is particles and which mathematics you don't believe is particles, right? If you're looking at quantum field theory, right? They're just these soliton type vibrations in this mathematical substrate. And so the question is there correlations between how we're describing it in one kind of mathematics and the same and similar kind of mathematics that they're describing the same stuff in another mathematical convention? So again, I'm not the reason I've done this because I hated Hilbert space. I thought the mathematics was vague and, you know, it hides what it's trying to do. Maybe it's concise, but it's for an engineer's mind, it wasn't. So I had to invent geometric algebra tools so that it was something that looked more like Boolean algebra in order to even make any headway on this, okay? And the good news is it was novel enough to get a PhD from it, okay? And which is important. And I had a professor who was a physics professor who wrote a book on physics and math for engineers, Cy Cantrell, who was my professor and he was from the physics department, but he was working in the engineering department, and he was my dissertation advisor, and he kept me honest the whole time about trying to match it up with what we already knew about Hilbert spaces. And so you can see in my dissertation, I always do the correlations with everything they did with quantum computing. This is quantum computing now, not particles. Quantum computing, and everything I did with quantum computing matches exactly what there's a correlation to with what they do in Hilbert spaces. And then Mike, 10 years later, says, I think these are particles. And so we, you know, Mike and I kind of believe it, but hey, we could use some input from other people that says, okay, how do we show that this is a particle? And one of the examples I think is the Bell operator assumes that once you get into this Bell state, that you can actually rotate among the Bell states. It's not just like enter into one of those states and that's it. You know, you can actually move around them. Well, that operator says, I have to apply an operator to both ends of the Bell states at the same time in order to do that. Well, it's hard to do that when they're not near each other, right? So the question is, I predict that there is an experiment here that could show that the mind could do that. And I could switch from one kind of Bell state where I'm aligned, where if you measure one, the other one's the same, to be counter-aligned. And I could do the equivalent of Dean Radin quantum, but do it with a Bell state and show that I could switch from a aligned to non-aligned state using the mind, because the mind is in the space where I can have concurrent states. So there's a concrete experiment that says I could do that if the mind would allow me to do concurrent Hadamard transforms. So how is that for physics?
Fair enough. You said one thing that sort of registered me. You said some kind of soliton vibration. What would this vibration look like?
Yeah, that's why we're working on Majorana and other stuff. We're looking at how to embed the same topological pattern in higher dimensional space. And Mike believes that you can look at if a bivector looks like a magnetic primitive and a trivector looks like an electrical primitive, then you could model a photon traveling through space-time as a 5-dimensional space that has a bivector and a trivector, and it keeps oscillating by applying the pseudoscalar to it, and it keeps oscillating between this bivector and this trivector and the other bivector. So it's all about embedding these patterns now in higher dimensional spaces is the way we would get to a model for quantum field theory and that kind of thing. So hopefully that answered your question. It's all about embedding it in a higher space. That's where we're going next. So.
Thanks.
Okay, Lou?
So, speaking of mind stuff, it seems you're suggesting that mind can do unitary transformations without collapsing the wave function, without causing an observation,
Yes.
and that seems like deep intuition in some level, at some level, and where would it interface with the physics?
Yeah. Well, I've talked about it in my previous talk about, Dean Radins. He's from the Institute of Noetic Sciences. He's an engineer, PhD engineer, like I am, electrical engineering, working on metaphysics, but he's an engineer, just like me. And he basically showed that you can have electrically isolated Faraday cage box that has a literally a double slit experiment in it, and people on the internet can take turns to influence the double slit experiment so that the probabilities change. And it's in an isolated system, and it's only quantum states. There's no electromagnetic field to be had there, So it's not like you can even account for it using electromagnetism. It's just literally pure quantum states. So my belief is if the mind can directly interact with quantum states, then let's predict some other experiments that have, like the Bell statistics are, that you can't get that result from those statistics unless you have unless you can describe the phenomena in a way that can give you like Bell statistics. And the same thing is true for other stuff. The experiments that they did with PK experiments and even remote viewing experiments, you can show that they have unusual statistics. Those statistics aren't possible unless you have a model for it, just like Bell statistics are. And so we have to have a model for explaining that kind of unusual statistics because classical statistics don't give it to you. So.
Doug, can I ask you a question relating to something that Mike actually said in his presentation?
Sure.
He made a comment about agent-based modeling, and I wanted to ask him when he said it, and it's more obvious actually with you presenting this stuff. Basically, he felt that his approach to computation was far more sophisticated than anything people are doing in agent-based modeling. I would guess you'd probably say the same.
Well, Mike has been working on Topsy for a long time. I'm assuming you're referring to a Topsy, right? Yeah, and his model is all about how to express concurrency that when you put the concurrency on top of each other, it doesn't fall apart, right? And you can't do that with regular computers. So there's got to be some kind of low-level concurrency control mechanism that scales as you go up the hierarchy, essentially, because every learning system, every agency system has some kind of hierarchy to build abstractions, right? So that's what his Topsy system is all about. And it's because the multi-vector has an orientation. That orientation feeds into the next level, and that's how it happens. And if you think about it from a physics perspective, low-level things are changing, but the multi-vector might not change because it may block the changes for the multi-vector based on small changes in the input. So as you ripple up, time actually slows down for changes that you see at the level above you, but you have this sort of space-like states, because if you have 1,000-dimensional state space and they're truly simulated using hyperdimensional orthonormal vectors, which is everything that Mike and I are doing, you can't embed it in a 3-dimensional space. So he's trying to give you a mathematical model if you're simulating consciousness or simulating intelligence, excuse me, so that we can simulate it using that. The big difference between what Mike is talking about, what I'm doing, is that I'm more interested in the real intelligence model that says, well, unless you actually have a high dimensional space, you're only simulating it. You only go so far. It's the quantum supremacy equivalent to real intelligence. In other words, that there's a limit to how far you can simulate, and it stops behaving like you want it to because you can't simulate it anymore.
Yeah.
So I think anybody who's not working on using real hyperdimensional space,
Yeah.
they're going to run into the quantum supremacy issue for intelligence.
Yeah. But the tools that we make, and particularly software like your software, really helps us along the way, doesn't it? You know, as
It
soon as
helps
we
us
have
to
these bits of
simulate
software
it.
which are created in consciousness,
Yes,
we're at a
they are
different
models of what
stage.
might happen. Yes, yes, I would agree with that. It's a model of what would happen. But remember, we don't have space-like states in our simulations.
Right.
You know, and so what happens then? You know, and we don't actually have 1,000-dimensional orthogonal space except simulating it. You know, and that's a problem. And that's why quantum supremacy is a thing, is because you take 2 to the 50 qubits, and 2 to the 50th qubits is more states than you can represent in a computer, especially if you have to have a matrix operator for it, which is squared. You know, 2 to the 50th squared matrix. Even if you do it sparsely, you can't simulate it anymore. So.
Yeah. Okay. It really is fascinating. I did lose you after about half an hour, but I was quite pleased that I got that far. So I'll
Yeah.
try and get further. Richard,
Yeah.
you're
You have
muted.
to unmute Richard, please. I'm sure it was a good question too.
It still is a good question, absolutely. I muted because I had a telephone call I needed to deal with.
That's great.
The question of terminology, I think this is similar to Anton's question. You talk about qubits, and I'm thinking of a quantum computing qubit as a thing that can simultaneously, say, do the entire sine table for our numbers between 0 and pi. And I don't see how I pull that out of the algebra that you're illustrating.
Yeah. So in my dissertation, I talk about, if you look at the general version of geometric algebra, you actually have a phase angle other than the corners. So you actually have a phase angle other than 0, 190, you know, 90, 45, stuff like that. So you can generalize this. Of course, it slows it down significantly if you do that. That's what Chris Doran did. And Chris Doran is the guy from Cambridge who wrote a piece of software that does ray tracing in 3 dimensions. And it was so good that you could like light a candle in a simulation and it would light the room naturally without doing post-processing. And ARM bought his software and is trying to put it in gaming theory. So just realize that this stuff is, you know, he's trying to figure out how to use it too. He's just a lot smarter than I am. So I'm working, again, is good for me.
Okay. So this ray tracing.
You can generalize this stuff. It just, I want to put all this stuff on a memory card like they use for gaming, and so I can parallelize it, you know, and do it in a where I can actually run geometric algebra in, you know, massively parallel, and we could even implement Mike's TOPSY that, and you know, as a way of like speeding up the performance of it. So.
Okay. So is this a correct statement that what you're giving us is what would happen if you took the real number system to zillions of dimensions and collapsed it to zeros and ones?
Essentially, we're looking at the corners of the spaces where bits are the primary dimensions of the space and just mining that for all the data we can. And entanglement is included in that. And again, it looks just like Hilbert space. It just has a slightly different meaning than the Hilbert space notation, knowing that there's really bivectors and trivectors in there. But you get, like I said, you get everything for a regular qubit, you get everything that's there for a qubit. You get trines, you get polystates, you get Toffoli gates, all of that stuff is in my dissertation. You get all this stuff the same way as you did quantum computing. Now, quantum computing is different than quantum physics, right? Because it's abstracted away from they're just looking at the quantum states. But so I've been focusing on quantum computing, not quantum physics. So hopefully that, and looking at it in restricted sense of, you know, even quantum computing focuses just with complex numbers, and that's a unitary constraint too. They're only going plus and minus 1, plus and minus I. You know, they don't go to 2. So we're not doing much different than Hilbert space is. That's just I've gotten rid of the complex numbers and used the spinner as the complex number. So that's the only difference.
Okay, Lou?
Another way of putting what you're doing, I think, is that in the usual way of speaking, we have a vector space, you have the Hilbert space, and then you have all the different tensor products of that space with itself that you're using for thinking about composite interactions.
Right.
And you
Right.
bundle them all up into the one geometric algebra,
Right.
and that lets you move freely among them all, and gives you a very nice algebraic
Yeah.
advantage.
And the verb nounness of it, where you can use an operator, something as an operator and a state, and that shows up in our what we're doing with the Tacorians. Essentially, Tacorians, you can't express that in Hilbert space, because here you have a Bell operator in conjunction with the Bell and magic states, and you're combining them to form a state that you can't express if you only have column vectors and matrix math for the operators and states in the states and operators in Hilbert space. So I wouldn't know even how to begin to do that in Hilbert space.
Okay.
Well, it was fun talking to y'all again and about this, and I had fun preparing this for it, this session, because, and I put some slides together, as you could see, just so that I would not get lost too much down too many rabbit holes, and I'll make that slideshow available too. So.
Yeah, I think
You'll send us those slides.
Yeah. If you go to quantumdoug.com, it'll be listed at the top there. As soon as Mark puts it there, I'll have a link to the other two talks are already there, and the PowerPoints are already there for the other two talks. And so just go to quantumdoug.com right at the top, and I'll put this one there as soon as Mark distributes the video.
This video is particularly valuable, Doug, because obviously not only are you dealing with some very important concepts, but you're doing it in a practical way where other people can follow and do the same thing for themselves.
You can do it. You can do it. Gave you all the tools to do it.
Yeah, so that's really great.
One more question. Yeah. Doug, you mentioned several things that were not invertible.
Mm-hmm.
So I'm wondering, could you extend it to the equivalent of a Moore-Penrose inverse?
Say that again. It's just a
More. You mentioned some non-invertible objects.
Mm-hmm. Non-invertible, yeah.
Could they be extended in the way the Moore-Penrose inverse extends inverting a matrix?
Well, it's not that I don't know how to invert it, as is the case with, you can show it for some smaller cases in G1 and G2, but in G4 with the Bell operator, I went through every corner of the space, all 43 millions. It says, is this thing, which is the total algebra of all possible things in the expression, will it give me an inverse? And the answer was no, it's not. None of those were the inverse. But the big deal was, and you can go to page, in my dissertation, you go to page about 110, I actually have a proof due to page 117, where I prove that you can't have a multiplicative inverse because of a contradiction in a summation of terms. I mean, you're simplifying two left-hand and right-hand expressions, and you get something that's as a result of that. It's so it's a finite constraint proof that proves the same thing that I did by exhaustion by going through 43 million cases. So
yeah, I don't think you answered my question though.
Okay.
So I put it in the chat. If I have a 2x2 matrix, diagonal matrix, with a 0 on one of the diagonal items, the inverse of an ordinary 2x2 matrix, you invert the diagonals and you're done. And for regular any matrix, you do the eigenvalue decomposition and play with the diagonal. So here, the Moore-Penrose says you invert the numbers that you can handle and you put 0 in for the others.
Oh, okay. So that's
Is there an equivalent to that in what you're doing?
Yeah. I don't know if it's possible to do that because I don't have other than corners. So.
Go ahead, Lou.
Yeah, Lou, if you can add to that.
A comment about inverting. You're going through all that because you want to show that there is no inverse element in the algebra,
Yes.
right?
Yes.
But on the other hand, it, maybe you can reformulate it as a matrix and then show that as a matrix it has an inverse or doesn't have an inverse in the larger space of all possible matrix operations. If you showed in the larger space that the determinant was non-zero, then it couldn't then it would have to be I'm sorry, that the determinant was zero, then it would be
It was
not
not.
invertible, right?
Except if you play games as I indicated. And
Well,
get a partial
is
inverse.
he subsampling? I mean, this technique looks like he's throwing away some information to get it to an approximation of an invertible matrix.
Well, you're inverting within the subspace that
Okay.
the inverse is
Yeah.
defined.
Yeah. Well, you can't create a smaller subspace for this because you lose the entanglement properties. I mean, one of the things that's interesting about this is that if you have an entangled space, which is what you have to have 4 dimensions in both Hilbert space and the geometric. You have to have 4 dimensions to get, in other words, there isn't enough topological room in a 3-dimensional space to have entanglement. It only shows up. It's like a knot. You can't have a knot in only 2 dimensions. You have to have 3 dimensions to have a knot. And if you have 4 dimensions, the knot pulls apart. So topological constraints are important. In entanglement, you have to have at least 4 dimensions for it to be entangled so that you can get this equivalent of a qubit embedded in a higher dimensional space. And you can't do that in 3 dimensions, and you can't do it in 2 dimensions. So the only time entanglement shows up as a topological subset already in a 4-dimensional space, and you can't simplify it anymore to do that. It's the same is true for Hilbert space. You can't do entanglement unless you have 2 qubits, which is 4 dimensions. So there's nothing different about that.
Okay.
Most mathematicians just wave their hands, thinks, oh, this is just math. But those dimensions are real, and you can't just compress them. You can't take an entangled state. It's just going to compress it to a whole and make it 2-dimensional, and it still is going to be the same. It isn't. You can't do that. It doesn't work. It's not entangled anymore if you've done that. So, but thanks for
Okay.
your attention, Mark. I appreciate you letting me speak again today.
Absolutely, but it's a pleasure, and it's been a revelation, and the tools are fantastic. So thank you very much indeed. And okay, so tomorrow we've got Wolfgang, who has unfortunately had to go to the doctor today, but he's going to be fit and well to talk to us tomorrow.
What he said, yeah.
And I can't remember what he's going to talk about. As someone got the program, they can probably find out. But I'll see you tomorrow. And hey, we're nearly there, you know. We're nearly at Friday.
He says, adding the conscious observer in physics using special
Right. Well, there we
relativity
are.
as an example.
Okay. Thank you.
Yeah.
Okay. So we'll see you tomorrow. And
Thanks, everybody.
yeah, look forward to it. Okay.
Thank you.
Bye-bye.
Thank you.